I am Exaucé, Luweh Adjim Ngarti. I am from INRIA. It's a lab in Grenoble, France. Today, I will introduce you to deep generative models. To start, what is a deep generative model? What you need to know is that a generative model is a model that learns a data distribution from observed sample and then generate new sample that are realistic to the observed sample. So the important thing to know here is that a generative model is just learning a data distribution. So we have a sample and we need to learn the distribution of the sample so we can generate a new sample. For example, here we can see in blue, there are samples for 1D distribution, and we can learn, for example, the density of this distribution. And from this density, we can, for example, sample new observation. So we can, for example, learn the density or just learn a generator that give us a new sample each time you call it. So there is two ways to build a generative model. We can approximate the density or build a generator. Why we need generative model? For example, here we can see that if we learn a distribution of human faces, we can generate a new image that is the image of a person that doesn't exist. Or we can also use it to generate, for example, a beautiful paint. If we train the model or other tableau, so we can generate a paint. Or another application is anomaly detection. Since we already know the distribution of the data, for a new data, for example, the data in red, we can see here that it's out of distribution, so we can realize that it's like an outlier. Another application that I'm working on for my PhD is a weather forecasting. So when we try to predict the weather, we have a numerical model, and sometimes we just generate multiple input to do multiple forecasts, and from this forecast, we try to estimate the statistics of the state. But what we can do with generative model, we can just generate few samples and learn the distribution of the state. Then we can just generate new sample or do a forecast with uncertainty quantification. So we already know what is generative model. It's just a way to model this data distribution. And we also know that we can use it for different kind of application, to generate new image, or for anomaly detection, or for weather forecast. So the goal of the talk is to give an intuitive overview of generative model, and also to prepare for the practical that will come next. And also, we will have an online session that will go deeper into mathematics. So this time is just to introduce the models, then we can go deeper in the online sessions. And I would like to point out that we will not cover language model. There is still generative model, but there is session tomorrow on language model. So first, I will introduce long-term variable model, VAE and GANs, and also normalizing flows. And also I'll do a quick overview of diffusion model and flow matching. Then we'll talk a little bit about how to do a conditional generative model. So the first latent variable is VAE, but first let's start with a classic autoencoder. So the goal of autoencoder is to learn a lower dimension future representation of, we have a future, and we need to learn a lower dimension representation. So the goal of the encoder is to reduce the dimension of the input, and the decoder, the goal is to reconstruct the input from the latent representation. So we can train with this loss that we just write that the reconstruction is close to the input. But the problem with autoencoder is that there is no probability here. The latent space is discrete. It is not deterministic. And also, we don't impose a structure of latent space, so we cannot generate new sample. That's why VAE comes. The idea is that for a new observation, we don't encode the latent representation, but we encode the distribution of the latent representation, then we decode it. So to train that, we still minimize the reconstruction loss. So the input and the output are close, and we add regularization loss to force the latent space to have a structure that we need. And usually we use just a Gaussian. So most common, we can use different reconstruction loss, but typically in a Gaussian likelihood model, it's just the MSE. And the regularization is often a callback divergence. So you force our latent space distribution to be close to a Gaussian distribution so we can sample from it. So I will ask if, like, when you have your VAE that is trained, you can use it for different kind of application. For example, imagine you have a website that asks people to upload their identity photo. And the question is, how can we check if an uploaded image is not actually an image of a person? So what we can do is to build a data set of human faces, and we can learn a VAE on this data set. So we have an encoder that is learned to encode human faces, and a decoder that is learned to decode it back to the image space. So when we have a new image, what we can do is to encode it and decode it. But if it's not a human face image, we can see that our encoder and decoder will not be able to encode and decode because it's training only on human faces. So if we struggle to encode and decode, we can say that this new image is likely far away from training data distribution. So the next generative model are GANs. And the idea of GAN is to just focus on the generative part. So we went a model that takes a latent value, like a small dimension value Z, and then to decode it to a space of observation that we went. So in the beginning, the generator is not good. So if we give it a latent value Z, it will give us a fake image because it's not trained already. But the idea of GAN is to train the generator jointly with a discriminator. First, the goal of the discriminator is to distinguish between the true and the fake image. So the first step is to train the discriminator, so you'll be able to distinguish if this image is fake or real. And when it's trained, the next step is to train the generator to fool the discriminator. So we force the generator to generate a new image that is close enough to the true one, so the discriminator is not able to distinguish between two. And the idea is to repeat this step until we converge to a situation, a discrimination is good enough to distinguish between true and fake image, and the generator is good enough to generate an image that can fool the discriminator. And to train the GANs, the loss function is just a min-max because we have two steps. First, to train the discriminator, then to train the generator. But all of the models that I present are generator. They generate new sample, but they actually don't give us the exact density of the observation. So we have normalizing flow, and the idea is that we can start for a simple distribution, like a Gaussian. We can apply from him like a invertible transformation, then we can transform it to a more complex distribution. But the transformation must be invertible because to sample from a new, to generate a new sample, we start by generate a sample from the simple density, then we transform it through the inverse of the transformation to have a new observation. And also, we can see here that since the transformation must be invertible, the input and the output space must be in the same size. So here there is no latent representation. We take like a base distribution in the same space and we transform it to the observation that we want. And the formula, the change of variable, can help us to get the exact log density of the transformation. And we can try to maximize the log density through the training. But normalizing flow can model like complex distribution, but when we try to sample it, we do it naively. The first image, we can see that in the yellow are the true distribution and dark blue are the sample. So when we try to sample, we generate sample even in the space where there is no density mass. So we generate samples that are not following the distribution that we are trying to model. The problem is that when you take like a density and you transform it with a continuous diffeomorphism, we cannot split it to a separate a multimodal density. You still have some space when you put density to connect the two modes. So there are the limitation of normalizing flow is that they have the sample problem, and also in higher dimension, you need to stack a lot of transformation to come from a simple Gaussian to a complex density. So there is this work did by Cordoue and Toulouse, and the idea is to train a normalizing flow, but when we are trying to sample, we can use like MCMC or other sampling approach. So jointly, we can improve the sampling of normalizing flow. So for this reason, a lot of people lost interest in normalizing flow because we have few models that are better in generation, but new paper show that they still very capable generative model, and they can allow to model complex distribution, and also we still have the exact density, so we can use it in more complex application. So the idea they did is that they add a new step into the sampling to avoid sampling into the space with lower mass density. And also, they show that the result can be comparable to some state-of-the-art model. So, a well-known generative model is a diffusion, and I will do a quick review of this model. The idea is we can start from the image, then we can add a small noise, and we can train our model to predict this noise, so we can correct the image, the noisy image. Then we can reiterate this approach, we add noise, and we denoise the image. And we can do it until the final image is a noise. And since we learn the reverse process to go from noisy to clear image, we can then come for the last. We can start from the noise, and then we can apply the reverse process. Then we can come from noise to a clear image. But the problem is that we need a lot of steps. We add the small noise with the noise. We add the small noise with the noise. It can take a lot of space. So the the new approach based on the same approach, but here we can come directly from the noise to the data distribution by just apply like a velocity fields. So we can learn this process that can directly come from the base distribution to the data distribution. And since it's continuous, we can do a lot of space, a lot of step of noising and denoising, and show that this kind of approach are actually good to generate new image. So the second part, I just show how we can model data distribution. But today, if we go on internet, we have some website that you can write what they call it prompt, a phrase like beautiful cat doing machine learning, and it can generate kind of image. So how to train this kind of model? Here it's model that they mix language model and image generation model. The thing is that it is still a distribution modeling. So this time we don't try to model just the data distribution, but we are trying to model a conditional distribution. So we need a distribution of the data given the value of the prompt. And if we take the diffusion model, it is still the same thing in the forward pass. We take the image, we add noise, and we try to remove the noise. But this time, to remove the noise, we add the prompt, the phrase to the neural network that is trained to remove the noise. But the problem is that we cannot directly use the text into the model. So we can train the encoder that can come from the space of the text to numerical space. Then we can use it to learn the reverse process. But I will not go deeper into how to encode the text. Tomorrow's session on large language model will show us how we can encode from text space to numerical space. So the key takeaway is that VAE are generative models that learn to come from data to a latent representation, and then from latent representation, we can go back to the distribution space. And since we learn the distribution of the latent representation, we can sample from the distribution and then decode to have a new observation. And then we have GAN, that their goal is to train a generator and a discriminator. The generator try to generate realistic image, and the discriminator's role is to distinguish between true and fake image. And we can train them until they have like 1/2 probability to have like a good image. So the last one are flows. In normalizing flow, the idea is that we take a simple density, we apply it with a complex invertible transformation, then we can have a complex density at the end. And we can have the exact log density of this distribution. And the problem with normalizing flow are that they are difficult in high dimension because we need a lot of transformation to go from a simple Gaussian to more complex distribution. But new work show that they're still good enough, and we can try to improve them to have a better data distribution, because with normalizing flow, we can have the exact density instead of just a generator that sample a new observation. And then we have a diffusion. And the idea of diffusion is to take the true image, we add small noise, and we learn how to remove this noise. Then we reiterate this approach until we come from a clear image to a noise, to a full noise. Then since we learn the reverse process, we can take a noise and generate a new image. And flow matching do like the same thing, but it's like a continuous transformation. So we don't have a discrete step of diffusion, but we can come directly from a noise to a data distribution. And I also talk about conditional modeling, data distribution modeling. The idea is that we can just take the prompt or the text and code it into a numerical space, and we can use it to model a conditional distribution of the data. So this time we model a distribution of data conditional to the input. So what to take from this presentation is that a generative model is nothing else than a data distribution. Sometimes you just model the distribution of the data to generate new one, or we can model the conditional distribution so we can generate new sample conditional to the input. But you must notice that since we learn the distribution from sample, if the sample are biased, we will also biased distribution modeling. So it's important to have a good data that represent when the distribution that we try to model, so you can learn the true distribution. Another thing is that this model need a lot of computing resources to train. So you need to have the resources to train them. So some model like diffusion, they can take a lot of time. So there's a technique like this that try to reduce the cost, but they still need a lot of compute resources. So after this introduction, we will have the practical. So during the practical, we will see you will try to transform and augment images using generative model. You will also distinguish between real and generated images. And the last part will be on ethical consideration of generative model. And since this talk is introduction of different kind of generative model, there will be online session on each model that you can go deeper on how this model work and how we can use them. So here is the practical team. And after this session, you can come to the generative modeling practical.
Cool. Thank you very much, Exaucé. Round of applause. So we do actually have some time for questions. So thank you. You made a good talk. So does anyone have any questions? Put up your hand and I'll come and bring the mic. Maybe do like 3 or 4 questions. No? Okay, I'll start with one. You mentioned the bias in the models. Something interesting I read like maybe 2 days ago is if you ask a generative model to generate a picture of a clock or a watch, it always gives you 10 past 10. And apparently this is because watchmakers, and whenever they do any advertisements, they actually always put it at 10 past 10 because that's the best looking watch. You can kind of prove this for yourself. Go try and do a generative model. Sorry, I just cut off. Yeah, try to do a generative model. And I think it's a perfect example of that. If you even just look up watches, you'll see this. Do you know how to kind of combat that? How can we fix that?
Yeah, it's a good point because, like I say, we try to learn the distribution from the sample. If the sample is not representative enough, we cannot learn the true distribution. So if, for example, us in weather forecasting, a solution is to get a new observation. So you can put sensor everywhere to have to augment the data. But for example, for the watch case, we can just generate synthetic data to represent different cases, then we can learn on that. But the solution is to implicitly inject like bias into the model because we know that there's different kind of time, so we can just generate synthetic data, then train on that.
Thank you, that makes a lot of sense. I'm gonna hand over to you.
Hi, you mentioned at the beginning that you could use variational autoencoders to tell whether an image is fake or real. Why would you not use a convolutional neural network? Why would you use a variational autoencoder instead of a CNN?
Okay, thank you for a question. Like, we can try to predict if it's a good image or not. We can try to have a sample of data from true images and fake, and then we can try to solve a classification problem. But the problem is that you need to have a lot of representation into your data set. So if you have, the goal is to distinguish if it's a face image or not, you need to put into your data set all other images that they might put into your model, so your model can distinguish between the true or fake. But here, if you use VAE, you only need data from the category or if you need human faces, you need only data from human faces to train your model. You don't need to add image of socks or other things to try to predict if it's that or not.
Thanks for your presentation. I'm curious about generative models and then how they get to parrot their outputs. Say some organization that trains on customer data in quotes, and I'm supposed to generate images for my customers. How do you recommend avoiding the case where I'm spitting out intellectual property while still giving meaningful output at the end of the day?
Yeah, can you phrase your question because I didn't.
Okay, so my question is, with generative models, how do I potentially avoid copyright infringement where I'm generating directly from customers' data?
How to avoid copywriting?
Infringement, since generative models would generate based on the distribution, right?
Yeah.
And then at inference time, you want the output to be meaningful, and you don't at the same time want to spit out what some customers spent their time designing in your software, for example. So my question is, how do you avoid cases like that where you are basically giving someone's artwork to the public through some generative model while at the same time doing something that's meaningful?
Okay, thank you for your question. I think it depends on the application, but the solution is not to build your own model, but you can take a big model, then additionally you can train your model giving the constraint that you have. So after you have the output for the model, you can apply your model to see if they follow the rule or not. For example, we work on generative model to generate poetry for kids. So we just take the model, but we train a new model that can try to constrain the output of the model. So if you have constraint like copywriting, you can just put it as a constraint out to the output of the model, so you are sure the output follow the rule that you like.
Yes, Vincent is my name. Question is, if there are images, what could be the sample size? And then you realize that if you tend to develop a model for maybe analysis or maybe trying to help maybe clinical decisions, if I don't have enough data, for example, images collected for a particular, I don't know, disease or something, what could be the sample size? And then if I have that sample size, can I generate more images to do the analysis that could help maybe make better decisions and all that? Thank you.
Okay, thank you for the question. I think there is no fixed answer to this question because it depends on your model. So if you have a big generative model, it can memorize just your sample data. So even if you fix the sample data, it will depend on the size of your model. So I think the good trade-off is to have a model that suits the size of the data set that you have. So if you have a small data, because you are in medical field and there's not a lot of data, you can still use generative model, but you reduce the size of model at the point that you will not be able to memorize just the data, but to learn real latent structure and hidden property of your data set.
Hi. So if you have a, in your diffusion process, and essentially what you're doing is you're adding noise, and you have these samples as you keep adding noise, and then you learn the way to go back. But if you have, let's say, two images that are close to each other, let's say two dogs which are very similar, and when you're adding noise, at some point, what you have is almost similar or the same. So then how do you know which way to go back?
Yeah. So the forward process, the way you add noise depends on the application. So if like low frequencies information, you need to control the noise that you add so you keep the information. But if the image are close enough, my question is worth it to separate them because they are already close enough. So it's normal to go from the noise to one of them because they are almost like collapse. So it's a normal behavior of the model. If they are close enough, you have some difficulty to generate a complete one. So I think we are interested more in different latent representation and feature of images than the small distinction between if the dog is sly or not. You can learn the more important feature first, then you can learn more to distinguish between the lower difference between the image.
Cool. I think we have time for one more question. So here you go. Okay.
Okay, thank you very much for the presentation. My name is Rodi Oswald. So I've been thinking about something. We said that generative AI is about generative new data or new samples of images from a sample of data of interested distribution, of a distribution we're interested in. Now I'm thinking of endangered species. We have, for example, cheetah, but we have also cat. Now, let's say we don't have any images of cheetah because we don't have any cheetah anymore, but we have only images of cat. But I don't believe there is a kind of similarity and resemblance between cheetah and cat. So we only have cat images, so we learned the true distribution of cat. Do you think there is any trick, I don't know, whatever, it can be latent space, arithmetic, whatever, but do you think there is any trick we can do in the embedding space in order to generate images that are quite close to cheetah while we learned the true distribution of cat?
Okay, thank you for a question. It's a good question. Here, cat and cheetah are all animals. So we can still use information from cat to describe a cheetah, like the number of noise and this kind of thing. So, for example, we can, for instead of coming from a full noise to a cheetah, we can transform the distribution of the cat that we learn to go to distribution of a cheetah. And in GANs, they used to do what they call cycle GAN, is to not start from a naive latent representation, but we can start from a distribution that we know. We have like a bias or a prior that this distribution is close to the one we need. So we don't need to go from a full noise. We can start from a distribution that is close for what we are trying to model.